Hey everyone, this is my solution video for quiz number 4, the reading quiz from July 15th. Alright, number 1. We want to calculate equivalent resistances of two types of circuits. A circuit with 3 resistors in series, and then a circuit with 3 resistors, the same 3 resistors connected in parallel. So let's draw out the circuit for part A. We have our voltage source of 3 volts, which we don't really need to worry about for this yet when calculating resistances. And then we have our first resistor, which is 5 ohms. We have our second resistor, which is 15 ohms. And we have a third resistor, which is 25 ohms. And what we want to find for part A, we want to find the equivalent resistance. That is, if we could reduce this to a single resistor, what would that resistor have a resistance of? And we want to find the current through each of these resistors. All right. So equivalent resistance for resistors connected in series is straightforward. It's just the sum of the individual resistances. This is just a fancy way of writing out R1 plus R2 plus R3, etc., until you get to however many resistors you have. So for this circuit where we just have 3 resistors, its equivalent resistance is just the sum of those 3 resistances. So we have 5 ohms plus 15 ohms plus 25 ohms, and summing those up, we get an equivalent resistance of 45 ohms. Now we need to find the current through each resistor. And now the thing to recognize here is that this is a series circuit, and series circuits are characterized by the fact that the current is the same through each element of the circuit. So whatever the current is in the circuit, each of these resistors is going to have that current passing through it. And we can find that current by applying Ohm's law to our equivalent resistance. So V equals IR, REQ, equivalent resistance, and then solve for I. I equals V over the equivalent resistance. So that gives us a current of, let's see, 3 volts divided by 45 ohms. And that gives us a current of 0.0667 amps. Or as that would often be reported in the lab or something, 66.7 milliamps. Alright, so that's part A. For part B, we need to do something similar, but now our 3 resistors are connected in parallel. So here's our voltage source of 3 volts, and then we have 3 branches, each with its own resistor. And I guess we'll keep these in the order they show up on the first one. This is 5. I'm going to didn't leave myself a lot of room here. This one's 5 ohms, this one is 15 ohms, and this one is 25 ohms. So there's our parallel circuit. So we want to find, again, the equivalent the equivalent resistance and the current through each of these 3 resistors. So the equivalent resistance in a parallel circuit is kind of like the equivalent capacitance in a series circuit. We need to we actually calculate first the inverse of the equivalent resistance, and then we invert that to get the actual equivalent resistance. So it goes like this. 1 over the equivalent resistance is equal to the sum of 1 over each of the individual resistances. So what we need to do in a parallel circuit is we need to put 1 over each individual resistance, add those fractions up to get 1 over the equivalent resistance, and then invert that entire thing to get the actual equivalent resistance. So for this problem, our inverse equivalent resistance is going to be 1 over 5 ohms plus 1 over 15 ohms plus 1 over 25 ohms. And that gives us 1 over the equivalent resistance of 0.306, etc. I'm not going to write that out exactly because I want to invert it before I round it for significant figures. So then the equivalent resistance, and the unit on this is actually the inverse ohm. Sometimes called kind of tongue-in-cheek, the mho. But that's just a silly physics joke. Anyway, so we want to find the equivalent resistance of this parallel circuit by taking this 0.306, etc., and inverting it. And doing so gives us the equivalent resistance of the circuit, which we find to be approximately 3.26 ohms. So that's our equivalent resistance. That's the first part done. So now we need to find the equivalent, the current through each resistor. And this is different in a parallel circuit than it is in a series circuit. And that's because in a parallel circuit, the voltage is the same through each circuit element. So that means that if we put a voltmeter on either side of any of these resistors, we will measure the same voltage. We should measure 3 volts across each of these resistors. But if we put an ammeter on either side of them and measure the current through them, we will get different currents. And it turns out, perhaps intuitively, that the lower the resistance, the more current goes through a given branch. Electricity is lazy. It likes to take the shortest, the easiest path, literally the path of least resistance. So to find the current in each of these resistors, we need to apply Ohm's law to each branch of this circuit. So that's not tough. Ohm's law is nice and simple. Sorry about my terrible handwriting. So we're going to apply Ohm's law to each branch of the circuit. So we'll call this branch 1, this branch 2, and this branch 3. So the current in branch 1 with the 5 ohm resistor is just going to be found by solving Ohm's law. For current. And that's just I equals V over R. Sorry. I don't know why I had that weird red part there. Okay, so for loop 1, or for branch 1, the current is going to be I equals V over R. And that's going to be 3 volts over the resistance of branch 1, which is 5 ohms. So that's going to be 0.6 amps. For branch 2, put subscripts on those so they're identifiable. We're going to have the same voltage over the resistance in branch 2, which is going to be 3 volts, now over 15 ohms. And that's going to be 0.2 amps. And finally, in branch 3, the current in branch 3 is going to be our voltage over the resistance of the resistor in branch 3, which is going to be 3 volts divided by 25 ohms, which is 0.120 amps. So we can see that each of the branches, because they have the same voltage to them, necessarily have different currents that are inversely proportional to their resistances. Lower the resistance, the higher the current in that particular branch of the circuit. So that's number 1. Okay, number 2. This is a Kirchhoff's law problem, or Kirchhoff's rules problem, sorry. And nobody likes Kirchhoff's rules. I don't like Kirchhoff's rules. I'm sure you don't like them either. But there's something you got to learn in order to properly analyze an electric circuit. So let's go through this. Now there are 2 rules when we're doing Kirchhoff's rules problems. First off is the loop rule. That is, around any closed loop of the circuit, the sum of the voltage drops and gains as you move through each element of the circuit is 0. And that's given to us by conservation of energy. The second rule is the junction rule, that the sum of the voltages going into a junction must be equal to the sum of the voltages leaving a junction. And that's a conservation of charge rule. Charge doesn't just appear and disappear at junctions. It has to split between branches in a way such that if we add those currents through the branches, we get the original current. So this particular setup is fairly simple. We have a setup with 2 voltage sources, 3 branches, and consequently 3 currents, and 3 resistors. This first one is 3 ohms, the second one is 4 ohms, and this one down here is 2 ohms. And then we have a 5 volt source here. Remember, the long thing on this symbol is the positive terminal, and the short one is the negative terminal, and that matters for choosing our sign on the voltage. I have the same down here, plus minus, and this is a 2 volt source. And finally, we have currents. We have current 1 taken to go this way, I1. We have current 3 taken to go through this middle branch, and we have current 2 taken to go through the bottom branch. All right, so that's our setup, and we want to find these unknown currents. So the first thing we should do is let's write down the junction rule. Junction rule is nice and simple. And there's only one equation from the junction rule. We have I1 splitting into I2 and I3. So therefore, I1 must be equal to I2 plus I3. Now for our loop rule, we want to construct a system of equations so that we have as many equations as we have unknowns. So the junction rule gives us one of these equations, so we need to use the loop rule to construct 2 more equations. Now there's how many loops are there? There's this loop, and then there's the whole loop that we could traverse. But we don't need to traverse all the loops in a circuit. We just need to trace enough that we have 3 equations and 3 unknowns in this case. Doing more than that is more work that we need to do, and it's redundant, and there's no point to doing it. So let's trace through the upper loop and the lower loop. And now when you're doing the loop rule, you have to be consistent in your direction of traversal. Doesn't matter if you choose to go counterclockwise or clockwise through the loops, as long as for each loop you go the same direction. Because that determines how you interact with the currents. All right, so let's traverse through the upper loop and the lower loop. And we're going to traverse through the lower loop, or I'm sorry, both loops. We're going to traverse through them counterclockwise. And we'll call this loop up here loop A, and we'll call this loop down here loop B. So let's traverse loop A. Doesn't really matter where we start, because we're going to end up where we we're going to end up back where we start anyway. So let's start by going through, let's start here at this junction where I1 breaks into I3. So let's see, we go through this resistor. Let me remember these resistors. We'll call this R1, we'll call this R2, and we'll call this R3, and we'll call this R2. Just for the sake of labels. So going through loop A, if I start at this point and I go to the right, I'm going to lose voltage. I lose voltage because I'm going in the same I'm traversing in the same direction as the current. And I lose a voltage equal to Ohm's law applied to this resistor. So I lose I3, R3. Now I'm going to keep going up. Now I'm going to go through this resistor too, resistor 1. R1 is 3 ohms. So again, I'm going in the direction of the current passing through this part of the loop. We'll take the current passing through this part of the loop to be I1. So I1 goes through this entire thing like that. So I lose a energy equal to I1 times R1. And then finally, I go through the voltage source. And I'm going through the voltage source from negative to positive. So I'm going through in the direction of the current, which means that I have a voltage gain of 5 volts. And then the sum of the voltage gains and drops around a closed loop is going to be 0. So I'm going to substitute in here, and I'm going to drop units and sig figs just for clarity's sake, just so it's really clear what's going on. All right, so the R3 is 4 ohms, R1 is 3 ohms, so let's plug those in. We get negative 4 I3 minus 3 I1 plus 5 equals 0. So that's that's our second equation in our system of equations. And we can get the last one by traversing through loop B. So let's go through loop B. And let's start at the same point. We'll start at this junction where current 1 splits into current 2 and 3. Excuse me. And let's traverse. So the first thing we come to is we come to a voltage source. But now we're going through it from the positive terminal to the negative terminal. We're going through it in reverse. So that means that instead of gaining 2 volts, we're going to lose 2 volts. So I'll write down as negative 2 volts. Now we go through resistor 2 of 2 ohms. Since we're traversing in the same direction as current 2, we get minus I2, R2. Loop around, and now we're going through the middle branch again. But this time, we're going through the middle branch in opposition to current 3. So instead of losing I3, R3, we'll actually gain I3, R3. And that's loop B. And that sums, again, to 0. So now, again, I'm going to substitute in numbers, leaving out significant figures and units just for the sake of clarity. So doing so gives us, let's see, negative 2 minus 2I2 plus 4I3 equals 0. And that is our third equation in our system of equations. All right, so let's write down our system of equations. I'm going to rearrange them slightly just so they're a little clearer. I'll get rid of this page here because it's covered in marker pressed through. Okay, so let's write down our system of equations. So our first one is just from the junction rule. We have I1 equals I2 plus I3. Then from loop A, we have negative 4I3 minus 3I1 plus 5 equals 0. So I'm going to move stuff over now just to get rid of negative signs and make this a little clearer. And I'm going to rewrite this as 3I1 plus 4I3 equals 5. And then from loop B, I'll do something similar. We're going to get, I'll write it like this. negative 2I2 plus 4I3 equals 2. So there's our system of 3 equations that we need to solve. Solving systems of equations is always kind of it's more of an art than a science. You have to know what tricks to use. This one should be pretty straightforward because we already have I1 in terms of I2 and 3, so we can just plug this in to I1 here. Or we could also add individual equations together. There's a couple different ways to go about this. I'm going to do this way. I'm going to take I1 equals I2 plus I3, and I'm going to substitute that into here. So that gives me 3 I2 plus I3 plus 4 I3 equals 5. And so simplifying that out, we get 3 I2 plus 3 I3 plus 4 I3 equals 5. And then combining like terms, we get 3 I2 plus 7 I3 equals 5. All right, well, that didn't give us a heck of a lot. But now we can solve for I2 in terms of I3 or I3 in terms of I2. I'm going to pick, it doesn't matter that much, but dividing by 7 is worse than dividing by 3. So I'm going to solve this equation for I2. So I2 equals 5/3 minus 7/3 I3. So we have an expression for I2. What do we do with that expression for I2 in terms of I3? We'll plug that into the bottom equation. So let's see, we've got negative 2 times 5/3 minus 7/3 I3 plus 4I3 equals 2. So let's see, we'll have negative 10/3 plus 14/3 I3 plus 4I3 equals 2. And combining like terms, 12, 3. So we have 26/3 I3 equals 16/3. Or 26 I3 equals 16, and therefore I3 equals 0.615 amps. So we've got a current. We now know the current moving through the middle branch of this circuit. And really, once you find a numerical value for one of the currents, it should be pretty easy to go through, substitute that numerical value in to the other equations to get out the other currents. So we know that I2 is related to I3 by this. So let's plug in that 0.615 amps into this equation for I2. So we get 5/3 minus 7/3 times that 0.615. And we should find that I2 is equal to 0.231 amps. So that's I2. And finally, we can get I1 by combining the two. So I1 equals I2 plus I3. That gives us 0.846 amps. So that's our final current. So let's just summarize that. I1 equals 0.846 amps. I2 equals 0.231 amps. And I3 equals 0.615 amps. Was there a more straightforward way to do this? Possibly. I could have picked a different thing to solve for. I could have maybe added these two of the equations together to see what happens. Again, solving a system of linear equations is at least as much of an art as it is a science, but you should be able to plug through it, even if you take the long way around, you should be able to plug through it to get to the right answer. Oh, one last thing. You'll notice that all these are positive, so what that means is that we guessed the directions correctly on each of these branches. If we had guessed the direction incorrectly, we would still get the same magnitude, but we'd have a negative sign on the current. That's okay. It's okay if you have a negative sign on the current. That just means that we assumed the wrong direction. As it turns out, the magnitude is correct. That's what we'd get if either way it's flowing. That's what we'd get if we'd say attached an ammeter to the current or to the circuit to read the current at a given point. So don't worry about negative signs on your currents. All right, that's number 2. And finally, number 3. So let's see. Number 3 tells us that in the lab, a student discharges a capacitor with a 2 microfarad capacitance by connecting it in series with a 1.5 volt AA battery and a 60,000 ohm resistor. So let's write those down. V equals 1.5 volts, and the resistance is 60,000 ohms, or 60 kilo ohms. All right, so the first thing we want to find is the time constant of the circuit. Well, that's pretty straightforward. The time constant of an RC circuit is just R times C. So, plugging that stuff in, let's see, we have our resistance, which is 60,000 ohms. We have our capacitance, which is 2 microfarads. Remember, we have to convert microfarads into farads, so this is going to be 2 times 10 to the minus 6 farads. And then we get the time constant. And turns out that time constant is 0.120 seconds. All right, so that's part A. For part B, we want to see how long does it take for the charge of the capacitor to drop to half of its full charge. So let's write down the discharging equation for a capacitor. Charge as a function of time is equal to the initial charge of the capacitor times e to the negative time elapsed divided by the time constant. Now here, e is the exponential, it's the natural exponential base, e equals 2.71828, etc. It's a transcendental number. It's the second most important number in math, constant in math after pi. It shows up everywhere in physics, mathematics, engineering, statistics. It's a very important constant. Here, it's just going to be a function that we're going to plug stuff into. All right, so we want to find how long does it take for the charge of the capacitor to drop to half of its full charge. That means that Q of t equals Q over 2. What does that allow us to do? It allows us to drop out that factor of Q. We don't, as it turns out, as long as we can express the charge of the capacitor that we're interested in in terms of the max charge, we don't have to worry about what the actual max charge is because they divide out. So let's substitute this Q over 2, big Q over 2, in for Q of t. So Q over 2 equals Q e to the negative t over tau. So we can just divide through by Q on both sides. And that leaves us with 1/2 equals e to the negative t over tau. So how do we need to solve for t, right? We want to find time. So how do we get that t down? Well, we need to take a natural log of both sides. So let's see, that gives us ln 1/2 is equal to negative t over tau. When you take the natural log of an exponential function, whatever's in the exponent just comes down. So I'll just write that as a reminder up here. Ln e to the f of x, whatever f of x is just f of x. That's just an identity you should keep in mind. All right, anyway, we want to solve for t. That's pretty straightforward. We move the tau over, we multiply by -1, and we find that the time it'll take is going to be negative time constant times the natural log of 1/2. So plugging stuff in, let's see, our time constant is 0.12 seconds. I'm actually going to leave natural log of 1/2 like this. Natural log of 1/2 is just going to be a constant that we know to arbitrary precision. It's like pi or the square root of 2. You don't need to worry about how many sig figs are in the natural log of 1/2. Just worry about how many significant figures are in your time constant. So negative 0.120 times the natural log of 1/2 gives us 0.0832 seconds. So it takes 0.0832 seconds, or about 80 milliseconds, for the capacitor to discharge half its charge. Turns out that capacitors with small time constants discharge their charge pretty quickly. And then finally, for part C is basically just a redo of part B with a different Q of t. So in this case, I'll keep this here just for reference. In this case, we want 1%. So that's going to give us little q of t is big Q over 100. So that's what we're going to substitute in for Q of t. So that gives us Q over 100 equals Q e to the negative t over tau. We need to solve for t. So you already know how to do that from up here, so I'm just going to skip the algebra here, and I'm just going to write down an equation for t. So t is going to be negative tau times the natural log of 1 over 100. Then plugging in our value for the time constant times the natural log of whatever 1 over 100 is, we should find that it takes 0.553 seconds for 99% of the charge on the capacitor to discharge. All right, that's it for quiz 3.